In this video, we are going to go over homework 1 for operations management. Let's start with question 1. We have a process diagram here. The number given in brackets is the cycle time for each step. So step B1 takes 10 minutes to process a customer. This is a barber shop. So B1, maybe there's somebody who greets the customer, gets their details, something like that. Step B2 takes 8 minutes to process a customer. And then we have this interesting split where we have step B3 being done by two different barbers. There is worker A. Worker A is perhaps newer. They take longer. They take 15 minutes to give a haircut, process a customer. And barber B is probably maybe more experienced or just faster somehow. They take 10 minutes to process a customer and give them a haircut. Then we go to step B4, where it takes 9 minutes to process a customer. Maybe they pay and give a tip and so forth. Okay. And we have to find the capacity of this step. So it's very important to understand what happens when you have two workstations and or workers working in parallel for the same step and they have different times. Okay. If you do not have two workers here, the diagram would be much simpler. So you would have something like this. So you would have B1 that goes to B2, that would just go to 1B3 because you have just one worker there, not two. Okay, B3, and that would just go to B4. Okay, so a simple linear process. And then if you had to find the capacity of this step, you'd have to find the bottleneck. So this one takes 10 minutes, this one takes 8 minutes. Okay. And let's say we have barber A, so this one takes 15 minutes, and just one barber, there's no barber B. Okay. And this one takes 9 minutes. So how would you find the capacity of this process? Well, you would identify the bottleneck, okay, which in this case is this is the bottleneck. Okay, step B3 because it takes the longest. So the capacity of the entire process will be capacity of step B3. So we could write it like this. Capacity of process equals capacity of bottleneck. Bottleneck is B3, so it equals capacity of B3. Okay. Okay. And so what is the capacity of B3? Well, we know that cycle time is 15 minutes and we need capacity in customers per hour. 1 hour has 60 minutes, so we divide 60 by the cycle time, which is 15, and we would get 4 customers per hour. Now we can't plug in 4 here because this 4 customers per hour is for this process, and the real process we have to analyze is this one, which is a little bit different. So what's happened here is that we have hired a second barber, which is barber B. And so we had this nice clean process with a capacity of 4 customers per hour, and we realized that step B3 is a bottleneck, so we hired a second barber. So the original B3 became B3A, and then up here we added a B3B. Okay, that's the second barber. And now if barber A is busy, customers will simply go to barber B. Right? And whenever they're done with barber B, they go to the station to check out. Okay? So essentially this question is asking, how do you analyze a process when you add a second worker in parallel to an existing worker, and the second worker takes a different amount of time because this worker takes 10 minutes. Okay? So that's what we have to understand. Now let me show you the simple case, and then we will actually answer this question. The simple case would be that barber B takes the same amount of time. And let's say they both barbers took 15 minutes. Okay, so let's do the simple case first so you understand exactly what's happening, and then we'll do this case where the two barbers take different times. Okay, so I'm gonna start clean. Let's make this bigger. Okay, so we have step B1, okay, and we have step B2, and we have step B3, and we have step B4. Okay, excuse my messy drawing, hopefully you can follow along. And the arrows show the direction in which the customers move through the system. Okay? And what I'm going to do is I'm going to write the number of workers, and for each worker the cycle time here. So step 1 has just one worker. Right? So I'm just going to draw a circle and two arms that represents the worker, and the cycle time, this worker takes 10 minutes per customer. That's 10 minutes per customer. Okay? B2 has just one worker, takes 8 minutes per customer, so just one person here, and this worker takes 8 minutes per customer. Okay? And now B3 is where interesting things happen, because we have two workers here, 1 and 2. Worker 1 takes 15 minutes per customer, and worker 2 in our simple example is also going to take 15 minutes per customer. Okay. And then we have B4, and we have just one worker, and they take 9 minutes per customer. Okay. So how do we analyze a process like that, where for one of the steps we have multiple workers, everything else is just one worker? Because if we were to say that the cycle time of step B3, so cycle time of B3 equals 15 minutes, that would actually be wrong. So this would be wrong. Why? Because cycle time is the time taken to process one customer. In step B3, what happens? Okay, so you get customer 1 with their wild hair being operated by the first barber, and customer 2 with their wild hair being operated at the same time by the second barber. So once 15 minutes are up, you don't output one customer, but you output 2 customers with their hair cut up. So every 15 minutes, step B3 can pop out 2 customers or 2 haircuts. Right? So 15 minutes cannot be the cycle time, because cycle time is the time taken to process one customer or one unit. 15 minutes we process 2 units. So what is the cycle time then? Cycle time for B3. What is it, right? So we say, okay, every 15 minutes we get 2 units of output, 2 customers. Okay. So how long do we take to output 1 unit? Well, if every 15 minutes 2 units pop out, if you calculate how many units pop out in a whole day or a whole shift, it will average out to 1 unit of output every 15 over 2 equals 7.5 minutes. Right? So 2 units coming out every 15 minutes on average is the same as a unit coming out every 7.5 minutes. If you have two versions of the process, in one version a stage pops out 2 units every 15 minutes, in another version that same stage pops out 1 unit every 7.5 minutes, and you run both these stages for a whole day or a shift, the output will be equal, because they're working at the same rate. The rate of work is 7.5 minutes per customer. Okay, so the cycle time for B3, okay, equals 7.5 minutes per customer. So you can just remember it like this: whenever you add servers or stations, these are the servers or stations, the workers. You add, if it's robots, you might add robots. If it's people, you might add people. If it's people plus an equipment, you add people plus the equipment. That's like a workstation. Whenever you add workstations, servers, workers, whatever you want to call them, as long as they can work independently and in parallel, the effective cycle time goes down. Now it's very easy to compute the effective cycle time if they all have the same individual cycle times. You just average them out. If there are 3 workers and each worker takes 20 minutes, we'll do 20 over 3, or 6.33 minutes is the average cycle time per unit, right? And so here you could just do 15 over 2, or 7.5. Okay? So that is how we can analyze this process now. So B1 has 10 minutes cycle time, B2 is 8, B3 is 7.5, and B4 is 9. So what is the bottleneck? Because bottleneck determines the capacity of the process. And you can see B3 is no longer the bottleneck because it's, averaging, it's giving you a cycle time of 7.5, not 15. And so 10, B1 is now the bottleneck. So this is now the bottleneck. So in this case, the capacity of the system, or in customers per hour, will be 60 over 10, or 6 customers per hour. So notice when we had just one barber taking 15 minutes, our capacity was 4. We added a second barber who also takes the same amount of time, and our capacity went up to 6. It did not double. Capacity of step B3 did double. So B3's capacity now is 8 customers per hour. Right? B3, if it runs out, it can do 8 customers per hour. It did double from 4. It was 4 before, right? But because B3 is no longer the bottleneck, B3 is going to be idle a lot of the time. B1 has become the bottleneck, and so our capacity for the whole process is 6 customers per hour. The whole process capacity did not double. Okay? So hopefully it makes sense. Now we're going to do the actual most complex case where we do have 2 workers working in parallel, but they take different amounts of time. Okay? So let's do that. So that's what the question is actually asking. Okay? So we have B1, we have B2, we have 2 B3s. Why am I writing them separately instead of just writing them like this, just show 2 workers here? Because when they take different times, I mean, you could represent it like this, right? You could just do one worker 15 minutes, the other worker 10 minutes. You could represent it like this, but I'm trying to draw the student's attention to the fact that you have multiple workers and they take different amounts of time. Right, because if I just had one box like this and put 2 heads here and gave different times, some students may not see the significance of that, and they might plow through the problem without really factoring in that there are 2 workers with 2 different times. So to make it explicit, so your eyes are just drawn to it and you factor that into the problem, I'm drawing these 2 boxes. You don't have to. You can just draw one box, put 2 workers in, like 2 symbols of workers, and give the cycle times of each worker. And that conveys the same information. The idea behind the process diagrams is to convey the timing data and the sequence of operations about the process, whichever notation you use, as long as the reader understands the notation, that's what matters, right? So I am picking this notation because it makes things very explicit. So A is a worker doing step B3, and B is another worker doing step B3, and they're working in parallel, which you can see from the diagram. After B2, you can go to either of them, whichever one is available. And then we have B4. Okay? So this whole thing just makes it very explicit. You don't miss out on the fact that there are 2 workers. And then if you look at the question, we have the cycle times 10, 8, then 15, 10, and then 9. So let's write them down. So this is 10 minutes per customer, 8 minutes per customer, 15 minutes per customer, 10 minutes per customer, 9 minutes per customer. So in this example, we had 2 workers taking the same amount of time. I could just average the cycle times to get my effective cycle time for stage B3. I can't simply average the cycle time. I can't do 15 plus 10 over 2 is kind of 12.5. Okay, so it's easier to work in capacities instead of cycle time. We can convert the cycle time to the capacity of each stage, and then the minimum capacity is the bottleneck, right? So what's the capacity capacity of stage B1. If they're only doing step B1, there was no other step before or after it, you just run B1 full throttle, the capacity in customers per hour will be 60 over 10 or 6 customers per hour. The capacity of step B2, okay, would be 60 over 8, okay, and that's going to be 7.5 customers per hour. Okay. The capacity of B3A, which is one workstation or worker in step B3, not the whole B3, is going to be 60 over 15, which is going to be 4 customers per hour. And capacity of step B3B will be 60 over 10, which equals 6 customers per hour. And then capacity of B4 will be 60 over 9, okay, which will be a little bit more than 6. So let's just calculate that. 60 divided by 9, 6.67. 6.67. Now, the good thing about capacity is it doesn't matter if the cycle times of the two workers in parallel are equal or not. Capacity always adds up when you have things are working in parallel. So whenever you have things working in parallel, okay, you simply add up the capacities, even if they're different, because the cycle times are different, so the individual capacities are different. So for this whole green box, okay, we can compute total capacity of step B3. That's going to be capacity of B3A plus capacity of B3B, which is going to be the 4 plus the 6. So 4 plus 6. And the capacity of step B3 is 10 customers per hour. Now, if we compare capacities, the bottleneck is the one with the lowest capacity. So 10 is definitely not the lowest capacity. So B3, the whole stage, is not the bottleneck. 7.5 is also not the lowest, so we have to compare this one, 6 and 6.67. So this is the lowest capacity, so this is the bottleneck, this is the bottleneck BT. So the capacity of the process equals capacity of the bottleneck, capacity of BT, bottleneck, okay, and that's going to be 6 customers per hour. Okay, you could use the same logic here. When you have two workers with different cycle times, just find the capacity of worker 1, which is going to be 4 customers per hour. Find the capacity of worker 2, which is 4 customers per hour. Because the two workers work in parallel, we add the capacities, and the capacity of step B3 is going to be 8. Okay, the capacity of B3 here will be 8. And so you could find capacity here, capacity here, capacity here, and you would have the you can identify the bottleneck as the one with the lowest capacity and do the same problem. So whenever you have parallel to a step being done by multiple workstations or workers in parallel, just switch to capacity. Capacity adds up when you're working in parallel. You find the lowest capacity, you find the bottleneck. The capacity of the bottleneck is the capacity of the process, right? You could, in this case, also average the cycle time, which as I showed you. But in this case, when you have different times, you want to find capacity and add up the capacity. And if you look at the capacity of 10, that means a cycle time of 6 minutes. So notice how you don't average the cycle time. 15 plus 10 over 2 is 12.5. But the effective cycle time of this stage is actually 6 minutes, right? Because the capacity is 10. And so you can't just average the cycle times to see what's going to happen, okay? And so this is the tricky part. You find capacity of this, capacity of this, add them up with capacity of total of B3, then you compare capacities to find the bottleneck and find the answer. So the answer to this problem is that step B1 is the bottleneck. It's going to drive the capacity of the process, and that's going to be 6 because that's the capacity of the bottleneck B1 in customers per hour. Okay, let's do question 2. What is the throughput time for a customer in minutes that goes through step B3A? Assume there is no waiting time before any of the steps. Throughput time by definition is the time taken when the customer starts here, goes through the entire process and ends here. What's the total time taken by this one customer? So you turn on the stopwatch when the customer enters the system, and you stop the stopwatch when the customer exits the system. The time shown in the stopwatch is the throughput time. Obviously, when the customer is waiting between steps, the stopwatch is still running, and so in real life, you add the waiting times to find the throughput time. But to keep things simple, I'm saying assume there's no waiting between steps. Maybe they entered when the shop was empty or something, and so let's find the throughput time. So the customer who enters here, they take 10 minutes to go through B1, so we have 10. Then they take 8 minutes to go through B2, so we have 18. Then we know they go through barber A, so we have to add 15 here. So 18 plus 15 is going to give you 33. And then they go through B4, and that's going to be 9. Right, so 33 plus 9 is going to be 42. So 42 minutes. Okay. And that's it for the Bill's barbershop scenario. So now we go to question 3. And here we have this process. To find the capacity of the process in units per hour. So this is really simple. There's just one worker at each station. We have the 4 stations. We have to find the bottleneck. To find the capacity of the process, bottleneck has the highest cycle time, or another way to say the same thing is bottleneck has the lowest capacity. But because we don't have multiple workers, anything complex, we can just find the highest cycle time here, which will be 8. For task C, so the capacity will be 60 divided by 8. So if you're using Excel, which I recommend you do, right? So for question 3, you'll do for question 3, cycle time is 8 minutes. So capacity in customers per hour will be 60 divided by 8, which will be 7.5. Okay. So we'll just put 7.5. So this was easy peasy, lemon squeezy. Let's do question 4. So we have a process shown below. The task time below each task are minutes per unit spent by the worker performing the task. Assume each task is being performed by just one worker. So same setup as before, like here. Okay, and then we have these times. What is the labor utilization for this process? Please enter your answer on the 0 to 100 scale and do not enter the percent sign. So example, labor utilization was 9.36%. We just enter 9.36. Okay. So to find the labor utilization, we have to find the bottleneck, which is task C, which is 8 minutes. Okay. And so what's going to happen is the utilization of the bottleneck will be 100%. At every 8 minutes, because bottleneck paces the process. So every 8 minutes, task C finishes the customer, starts on the next customer right away. All the other tasks which have a cycle time less than the bottleneck, less than 8, will have some idle time. So task B will spend only 4 minutes per customer, but then it will have some idle time because it will keep running out of customers because task C is slower than task B. So it will have idle time because it will be blocked by C. If there's no waiting area between B and C, once you pop out a customer and send them to task C, you can't pop out the next customer because they have nowhere to go because task C is still busy, and so task B now has to wait for there to be space to pop out the next customer, for example. If there is waiting space, once the waiting space is filled up, then task B will have to wait. So if you look at the lecture, we talk about starvation and blocking, which is the explanation of why the entire process runs at the pace of the bottleneck. So listen to that part of the lecture, understand what starvation and blocking are. The conclusion is that we're going to run at this pace. We're going to run at the pace of 8 minutes per customer. Okay? So to find the labor utilization, we are going to add up these times, okay, and then we're going to divide by cycle time times the number of tasks we have. Okay? So what we're going to do, and the formulas are given in the slides, what we're going to do is we're going to take the cycle time of each stage, so B, cycle time of A plus cycle time of B plus cycle time of C plus cycle time of D. And divide that by cycle time of whatever is the bottleneck, which in this case I think is C, but whatever is the bottleneck, okay, times how many stages did we have? So we have 1, 2, 3, 4 times 4. So that'll give you the average utilization for the process. Okay, so cycle time of A is 5. Actually, let's do it in Excel. So this is question 4. Okay, so we do C, cycle time A, cycle time B, cycle time C, cycle time D. So let's list them here. 5, 4, 8, 6. So 5, 4, 8, 6. Okay, so our labor utilization will be sum of these numbers. So 5 plus 4 plus 8 plus 6. Okay, divided by cycle time of the bottleneck, which is right here, times we have 4 steps times 4. Okay, so this is not in percentage scale, so we have to multiply this by 0 to 100 scale, to multiply this by 100, so we get 71.875% as our labor utilization. We don't have to enter the percent sign, we need 2 decimal places, so this will become 71.88. And so how did we come up with this thing? How did we do this? And all that is explained in the lecture, so review the appropriate part of the lecture for that. Okay. Question number 5. Spicy Stop Restaurant. Okay. So a restaurant has 4 chefs. The average meal takes 10 minutes to prepare, and a chef can cook 3 meals simultaneously. What is the capacity in meals per hour that can be prepared? So again, interesting question. So we have 4 chefs. Okay, so whatever is the capacity of one chef, right? If we knew that, if you knew the capacity of one chef and you have 4 chefs working in parallel, just multiply it by 4 to get the total capacity of the cooking area. Right? Because when things work in parallel, capacity adds up. So capacity of chef 1 plus capacity of chef 2 plus capacity of chef 3 plus capacity of chef 4 is your total capacity. Now, why can I multiply by 4 and not add up all 4? Because they're identical. Okay? The question says the chefs have identical skills and experience. Each chef works at exactly the same pace. If they were not identical, then you would do something like this. You would say total capacity equal capacity of chef 1 plus capacity of chef 2, because they're working in parallel, so capacities add up. Remember, when things happen in parallel, capacities add up. Plus capacity of 3 plus capacity of 4. That's what you would do if the chefs, one was a trainee chef, worked slower, one was a master chef, worked faster, things like that. You do that. But because the chefs are identical, adding the same number 4 times equals multiplying the number by 4, and so you can just do that. So I need to find the capacity of one chef. So what does one chef do? They cook 3 meals, and I have to find everything in meals per hour, how many meals we can generate in 1 hour. So one chef cooks 3 meals simultaneously, and it takes 10 minutes. Okay, so it appears that cycle time is 10 minutes, right? But that is not so, because every 10 minutes you're not popping out one meal. And the cycle time is the time taken to complete 1 unit, to process 1 unit, in this case 1 meal. So every 10 minutes, you don't pop out 1 meal. Every 10 minutes, you pop out 3 meals. So 10 minutes gives you 3 meals. So how many minutes would give you 1 meal? That'll be 10 minutes divided by 3. This many minutes, which is 3.33, will give you 1 meal. So this is the real cycle time. So cycle time is going to be 10 over 3, because 3 meals cook in parallel, which is 3.333, something like that. That is your cycle time for the chef. If this is the cycle time, what is the capacity in meals per hour? Because it's per hour, you take 60 minutes, you divide them by the cycle time for the chef, which is 3.3333, and that will give you the capacity of one chef. You multiply that by 4, you get the total capacity. So let's do this in Excel. This is question 5. Okay, so we find cycle time of a chef. They do 10 minutes to produce 3 meals. So per meal is going to be this. So that's minutes per meal. Okay, then we can find capacity of a chef in per hour. So 60 minutes by 3, that's where we do get a 60 from. That's 18 meals per hour. And then we need capacity of 4 chefs. They're identical, and so we just take this capacity and multiply it by 4. Okay, so this is just the units and meals per hour. Okay, so 72 meals per hour is going to be my capacity. Okay, so the Spicy Stop restaurant has seating for 50 people. On average, a customer eats one meal and spends 50 minutes seated. This includes time to order, get the meal, eat, and pay. So a customer spends 50 minutes in a chair, in a seating, and we have 50 seating total. What is the capacity of the seating system in meals per hour? This is a very interesting question. Okay, so we have these seats, 1, 2, and they're around tables, obviously, right? So there's a table, there's some seats around it, right? But wherever they are, total we have 50 seats. We're going to make the simplifying assumption that we can split tables, and maybe the tables are made of smaller tables, we can split them. So if a group of 4 comes in and a group of 6 comes in, we don't seat the group of 4 on a table for 8 and waste 8 seats. We just move the tables and chairs around, so the group of 4 only consumes 4 seats, and the group of 6 only consumes 6 seats. So we have 50 seats. This is the resources we have. Okay, for one seat, what is the capacity? For one seat, okay, the cycle time is 50 minutes. Okay, 50 minutes, because the customer sits in that seat for 50 minutes to consume a meal. So in terms of customers per hour, how many customers can one seat give you? And so the capacity of one seat in customers per hour, right, is going to equal 60 minutes divided by the cycle time, which is 50. Okay, so it's going to be something like 1.2 or something, but I'm just going to write it as a fraction. 6 divided by 5 customers per hour. Okay, 60 minutes in an hour divided by the cycle time, which is 50 minutes. That's the capacity of one seat. So what is the capacity of 50 seats? Because that's the total capacity of my seating system. Remember, when you have things working in parallel, capacity just adds up. So you take the capacity of one seat, you add it 50 times to get the capacity of 50 seats. Adding the same number 50 times is the same thing as multiplying it by 50. So capacity of seating system, which has 50 seats, seating system equals capacity of one seat, which is 6 over 5, multiplied by 50. Okay, and you can see now why I kept this as a fraction. The 5 will work with the 50. This will cancel out to make it 10, and you can do it in Excel. This will come out to be 60 customers per hour. Okay, so the capacity of my seating system is that it can handle 60 customers per hour. And it's very intuitive, because we have 50 seats. If a customer spent a whole hour in the seat, our capacity would be 50 customers per hour, but the customers spend less than an hour in a seat. So a seat can do more than one customer in an hour. So 50 seats should give you a capacity above 50, because the customers are not spending the whole hour in the seat. Okay. So now we have to incorporate information from questions 5 and 6 to answer question 7. Okay. The manager notices that the cashiers, the servers, the bussers have a lot of idle time and are not even close to being the bottleneck. Okay, so they are not the bottleneck. So what is left? What's left is the seating system and the kitchen. One of them has to be the bottleneck, if nothing else is the bottleneck. Demand has increased recently, with the restaurant now turning away customers due to lack of capacity. The manager is wondering what to do to be able to serve more customers. Which of the following options will allow the restaurant to serve more customers? Okay, and multiple correct choices are possible, so you can select multiple choices. So we have to evaluate each choice. So what is being asked of us is that we have these different stages. So maybe we have the cashier, whatever else stages we have. None of the stages is the bottleneck, except the seating system could be the bottleneck, or the kitchen, or the chefs. Like the chefs could be the bottleneck, and nothing else is the bottleneck. So if you look at the answers to question 5 and 6, capacity of the meal prep area is 72 meals per hour, or 72 customers, assuming these customers orders one meal. And the capacity of the seating system is 60 customers per hour. So the bottleneck has the lowest capacity. So which of the two is the bottleneck? Has to be the seating system. So the seating system has the lowest capacity, so this is the bottleneck. And so the capacity of my restaurant is the capacity of the seating system, which is 60 customers per hour. Now, if I add more chefs, can I process more than 60 customers per hour? No, because the bottleneck is the seating system. If I add more cashiers, can I process more than 60 customers per hour? No, because the bottleneck is the seating system. Unless you increase capacity of the bottleneck, you are not going to be able to serve more customers. The other you will just have more idle time. Okay. So let's see which options and how do you add capacity to the bottleneck. There are two ways. One is add seats, right? You can add seats to add capacity. And another way is to reduce the cycle time. Reduce that. If you start doing something faster, which is lower cycle time, you can process more customers per hour. So when you think about increasing capacity of a stage, don't just think about adding resources. Maybe you can just cut down the cycle time, and that will increase the capacity too. So we have to either cut down the cycle time of the seating or increase the number of seats. That is the only way we can increase how many customers we handle per hour until the seating capacity goes up to something like 72 or 73, in which case the kitchen becomes the bottleneck at that point. And then you have to add seats or something and add chefs to increase capacity beyond 72, right? But right now, while our capacity is at 60, this is the bottleneck. We have to attack this area. Okay, so let's look at our options. Firing one chef as an idle time in the kitchen. Okay, that is not going to increase your capacity. It may decrease idle time in the kitchen. Maybe the kitchen will become a bottleneck. They may actually decrease capacity because you have 4 chefs and you're getting a capacity of 72. If you fire a chef, you're going to lose a capacity of, 18. So you're going to go down below 60 and you're going to reduce your capacity of the system, and this is going to become the bottleneck. So firing a chef is a bad idea, but the main point is, will it let you serve more customers? No, it will actually make us serve less customers. So this is not the right option. Rearranging the open spaces to fit 12 more seats. Yes, it will add capacity in the bottleneck. And notice 60 plus 12 is 72. So that works. If you were adding 20 more seats, the capacity would not go to 60 plus 20, 80. It will still only go to 72, because after you've added 12 seats, the 13th seat gives you no benefit because now the kitchen is the bottleneck, right? Because that's stuck at 72. And so adding 12 seats will take your capacity of the seating system up to match the capacity of the kitchen. And at that point, both the seating system and the kitchen will be the bottlenecks. And so you'll have to increase both to go beyond that. Assuming nothing else like cashier or whatever else is not yet a bottleneck. Playing fast music, which speeds up customer eating by 15%. Yes, because it will cut down the cycle time. Currently, customers spend 50 minutes sitting in the chair, right? And if they eat 15% faster, maybe the cycle time goes to 48 minutes or 47 minutes or 45 minutes. It goes down, and so your capacity here will go up, because your capacity of the seating system is 60 divided by the cycle time. That's capacity of one seat times you have 50 seats. Right? So that's your capacity of the seating system. If this number goes down, becomes smaller, this number will go up. Your capacity would go up. So yes, this would reducing cycle time is always going to increase the capacity. Whenever you reduce cycle time of the bottleneck, you increase the capacity of the whole system. So this would work. Replacing one table with a nice fish tank. No, the seats are already your bottleneck. You throw out a table with 6 seats, you go down from 50 to 44 seats, you are hurting yourself. You're not making sense in terms of increasing capacity. So these are 2 of the answers. Now the answers may be in a different order for you, so make sure you select the right options. Last question. In a medical test processing lab, samples need to be prepared before being entered into the testing machines. At this preparation stage, there's a little bit of batch processing happening here, so a little bit of a taste of that. Cycle time is 90 minutes per 100 samples. So we have a batch of 100 samples. We spend 90 minutes making the batch. Multiple workers can work in parallel at this stage. If 3 workers are assigned to the preparation stage and each worker works an 8-hour shift, what is the capacity of this stage? So very interesting. So let's do this. So first up, we have 3 workers, right? So we have worker 1, worker 2, worker 3. There's no hint in the question that the workers are different, work at different speeds. They actually are working at the same speed, 90 minutes per batch of 100. So we can just find the capacity of one worker and multiply that by 3 to get the capacity of the whole system. So for question 8, we need to find capacity of one worker and then multiply that by 3. So what's the capacity of a worker? Well, a worker spends 90 minutes to make 100 samples. Okay, so how many it's like a batch of 100 samples. So how many batches will the worker make in a day? So the worker, one worker, so we have just one worker. Okay, how much time they have in the day? They have 60 minutes times 8 hours. They have this much time available. And every 90 minutes they finish a batch. Divided by 90, this is how many batches they will finish, right? So capacity of one worker is going to be 60 times 8 divided by 90. That's 5.33 batches per shift. We don't need it in batches, we need it in terms of samples. How many samples? In a lab, they have like blood samples or something. So you have to multiply this. There are 100 samples per batch. So you multiply it by the batch size and you get 533.33 samples per shift by one worker. Okay. Now, what is the capacity of this preparation stage? Well, we don't have one worker, we have 3 workers. So capacity of entire stage will just be the capacity of one worker times 3, because we're assuming workers are identical. The question does not give me any data to assume that the workers work at different speeds. If they did, you would be given, okay, worker 1 takes 90 minutes per 100 samples, worker 2 takes 50 minutes per 100 samples, and worker 3 takes 200 minutes per 100 samples. You'll be giving that different cycle times per worker, but you're not. So the workers are identical. So you find, how many samples per shift a worker does, times 3 is the capacity of the stage. So we can do 1600 samples per shift we can prepare. Okay. So that is it for homework 1. If you still have any questions, you don't understand any part of the video, rewatch it. You don't understand it again, email me to get help and I will explain what's going on to you. Okay. Hopefully the video is helpful and hopefully it will help you do well on the